So now let us move ahead with the concept of your oscillators. I have already told you, in fact, this particular triangular bar square wave generator is also considered as an oscillator because it generates the output voltage, whether it is a triangular or square wave, without taking any external input, right? So you know that whenever we don't take any external input, we get some output, required output or the desired output. We call them as the oscillator, right? So basically oscillator is a type of feedback amplifier in which the output is fed back via the feedback circuit to the input signal, right? And definitely if the input signal is fed back, if it is of some proper magnitude and phase difference with respect to the output, definitely it will start oscillating and it will produce a kind of output. And when we have discussed about the frequency compensation techniques, right? So the oscillations were undesired there, right? But that time, if you remember correctly, I had told that we deliberately sometimes make the circuit to oscillate because we want to generate either a sine wave or a triangular wave, right, or a square wave or different kind of waveform without providing any input to your circuit. So now if you look at the block diagram, let us see here, wait for a while. Yeah, if you look at the block diagram, now let me say that I have got an amplifier circuit here. You have already studied the different types of oscillators, maybe in your analog electronics, and maybe I have a summing circuit here which gives the difference in the signal Vd, something like this. So this is going to be provided to your amplifier. Let me take this gain as AV, and this is my V0, which is the output. Then from this, what I do is I take the feedback. I take the feedback like this. So let me call this as feedback circuit with a feedback factor, say beta, right? So then you have the signal here which is going to this summing block, and see here, this is a positive signal that indicates that this is my positive feedback. This is V in. Deliberately I will make it 0 because I don't want any input. So this is the summing junction. This is how you can have the block diagram for an oscillator, okay? And now here we will try to write some of the aspects, right, which we have already written. If you remember correctly, we had seen the Barachus criteria, right, when exactly a circuit is set to oscillate, when the phase margin and phase shift, right, so the gain and phase shift, what value they attain when the oscillator, the circuit start oscillating, that we have already seen. Anyway, we will look back again here, right? So your Vd here, this your Vd, okay, is so this is the feedback signal Vf. So you can say that it is V in plus Vf as long as some V in is present, and your V0 is equals to this V0, okay. It is AV into Vd, this AV into Vd, you can see here Vd and AV, okay. And your feedback voltage is V0 into beta or beta into V0. These are the things which you have studied long back, right? And now if I want to take the ratio of V0 to V in, if I want to take the ratio of V0 to V in, I will get this as AV divided by 1 minus AV into beta. I don't want to go into these details because we have already discussed these things earlier. So now if you take your AV into beta equal to 1, okay, which you can take it as 1 at an angle either 0 degree or 360 degree. So now you can say that we are in a position to have the self-sustained oscillations, provided your feedback circuit supports that, right? Suppose you have got an amplifier. When I speak about the amplifier, definitely your gain will be 1 or more than that. One condition gets satisfied, and the second condition, the phase shift should be either 0 or 360 degree as per Barak-Hussein's criteria. For the circuit to oscillate, so we have the gain AV should be equal or greater than 1, and the phase margin, phase shift, the total phase shift in the circuit should be either 0 degree or 360 degree. This is what we have seen, right? So now if you consider an inverting amplifier, obviously you will have a shift of 180 degree, and if your feedback components are able to provide another additional 180 degree phase shift, so the second condition also gets fulfilled. So this is where your circuit starts oscillating on its own. So you may have the circuit representation something like this. So this will be your amplifier, right, with a gain of AV. Then you have the output here. Okay, so then this output is fed back. This is the feedback with the beta, and this feedback, let us say that it will have small oscillations here, and these oscillations become sustained oscillations here at the output, right? So this is how the circuit without giving any input, so your V in is equals to 0, right? And how exactly it happens? So when there is no input, how it is possible to have it's a sustained output, you have already seen, right? Because you are giving the supply voltage, so that results in the initial small voltage because of the continuous feedback that gets accumulated, and you get the sustained oscillations. And for the sustained oscillations, there are several conditions to be fulfilled. That all depends upon what type of the oscillator circuit you are going to have there. Okay, so this is the simple philosophy behind the oscillators. Oscillator basically is a circuit which is in fact it is a feedback circuit. Without any input, it is able to produce sustained outputs as per the requirement. And the circuit components, whatever we have there, so those circuit components will decide the nature of the oscillation, right? So this is what is the basic about the oscillators. Now based on this, we will discuss about the different kind of oscillators, whatever they are mentioned in your syllabus, right? And again, please compare. When we discuss about the frequency compensation, the oscillation is not desired phenomena, because that will lead to the instability of the circuit. But here, from the point of view of the application, right, we are looking at the operational amplifier, so where the oscillation is one of the very prominent and important applications, right? So now the first one here is the phase shift oscillator. You have already studied about the phase shift oscillator, RC phase shift oscillator, using your transistor circuits. Now I just replace the transistor circuit by the operational amplifier here, right? So now when I speak about the phase shift oscillator, suppose if your feedback voltage is something like this, okay, you have the output something like this. This is the output, this is the feedback voltage, right? Please remember, many a times I have observed students giving the input to an oscillator circuit. That should not happen, right? So you don't give any input, it is the feedback, right? So now let us try to take the circuit diagram for this. I take the Opamp. If you are able to recall your oscillator circuits using transistors, so probably you will understand these things very easily, because the concept or the philosophy behind this you have already seen. VEE. Now look here, from the output I am providing the feedback in the form of R and C's. You can see here 3 capacitors and 3 resistances, and I deliberately have taken this resistance as a part of the ladder here, right? So this is connected to ground, this is connected to ground. So now this is R1, this is R2, this is R, this is R. In fact, R is equal to R1 only. So C, C, C. This is the simple circuitry as long as the phase shift oscillator is concerned. I hope all of you are drawing these things.
Yes, sir.
Yes. This is V0. And here the non-inverting terminal I will ground it. You should be able to understand here how exactly it works, right? You have got a total phase shift of 180 degree, and these combinations R and C, right? So each combination will provide approximately how much phase shift. You should be able to quickly recall these things. Approximately 60 degree, is it not? Each of this, the values of the capacitance and resistance are taken in such a way that each combination, right, in this ladder, they produce approximately 60 degree phase shift. Probably you have seen these outputs in your analog electronics laboratory also, in each case how much is the phase shift. So additionally you will get phase shift of 180 degree, so that total out of phase waveform you are going to get here, right? So basically it is inverting amplifier, right? So this provides a natural phase shift of 180 degree, right? And the RC components provide additional phase shift of 180 degree. So total phase shift is approximately 360 degree or 0 degree. So your Barack Hussein's criteria is satisfied. So the circuit starts oscillating on its own, and the very important thing is here the frequency of oscillation. at what frequency this circuit is capable of operating or oscillating, right? So that is decided by the values of R and C components, right? So based on RC components, frequency of oscillation. Of course, we can prove this if you take only this part of the circuit, right? Suppose now, anyway, you need not take down this. So we have got the output here, say V naught, then I have got R here, then I have got C, one more R here, right? So then one more C, one more R here. Okay, so let us take that it is Vf. If you take the ratio of V naught by Vf in the frequency domain, that is from the time domain, if you convert it into frequency domain, right? So you should be able to get the value of the frequency of oscillation, right? So that you need not take here, it is given in the book. There is a big derivation for all those things, so let us not go into those details, right? So to obtain 180-degree phase shift, to obtain 180-degree phase shift from RC components, right? So we should have XC is equals to root 6 into R. So this is the condition to be satisfied. XC is equals to root 6 into R. Okay, so this will give, it is given in the book. You can refer to David Bell, Electronic Circuits, or any other relevant books on electronic circuits. All these derivations are given. Since we are not there to go with the derivation here, so I am just writing these values. F is equals to 1 divided by 2 pi root 6 into RC hertz. This is the frequency of oscillation in a RC phase shift circuit. F is, please remember this, F is equals to 1 divided by 2 pi root 6 into RC, right? So now this particular circuit will also produce, apart from the frequency, the circuit, the RC phase shift network also produces an attenuation. You know what is the meaning of attenuation, right? It is the opposition for the flow of signal, right? Attenuation of attenuation factor equal to 29. So meaning is that the amplifier must have a voltage gain, right? The amplifier must have a voltage gain, AV should be greater than or equal to 29 for the loop gain to be equal to 1. This is a very, very important point to be noted, for the loop gain to be equal to 1, right? So because we have to have the condition satisfied here, Barak-Hussein's criteria, the total loop gain should be either equal to 1 or more, or the total phase shift should be 0 degree or 360 degree. If at all you want to achieve that, the amplifier should have a gain of at least 29. Otherwise, the very attenuation which this circuit is going to develop will not allow the loop gain to become equal to 1, right? So this is another important condition, and that definitely can be fulfilled by taking the suitable values of R2 and R1. So your R2 should be at least 29 times more than R1, then your total gain will be equal to 29. So this is what is the basic operation of the phase shift oscillator. We have taken the inverting type, you have got the output here. Inherently it is going to produce an output of 180 degree, but because of the feedback components which additionally put or introduce the phase shift of 180 degree, the total phase shift is going to be approximately 360 degree. And if you want to satisfy the other condition, the total the gain of the circuit should be at least equal to 29 or more, right? So you can see here, without taking any input here, your circuit is going to have the sustained output oscillations. That is the reason why it is called as the phase shift oscillator.